Hello. Today we're going to be beginning a new unit of modern physics. Now, before we begin with modern physics itself, we first have to start talking about light. See, light has an interesting story in physics and a long history of debating whether light is made up of a particle or made up of waves. So, throughout time, scientists have tried to piece that one together through experimentations and different theories. Now, this didn't start getting good until Newton got involved. He did a lot of experiments with light, and particularly how light interacted with glass and prisms. And through his experimentations, Newton theorized that light was made up of particles based on essentially how it interacted with these things. He had some cool ideas with how light interacts with our eyes, thinking that the different colors were associated with different sizes of the particles. Pretty cool stuff. However, not too long after Newton, another scientist worked with light and transverse waves and discovered that light had the properties of waves, had things like reflection and refraction, refraction being pretty unique to light itself. So this kind of cemented the idea that light was actually made up of waves instead of particles like Newton believed. Now, this theory got very, very good once Thomas Young got involved, and he did his experiment with diffraction and interference with light. Now, we did this experiment near the beginning of the year where we saw light bend and make interesting patterns. We can see this picture right here where light is making this very distinct ring-like pattern, and that's caused through interference and diffraction. Now, this is a very wave-like property, so at this point, it was pretty much cemented in everyone's mind that light was waves. Now, there's one problem with this idea, and that is how does light get from the sun to the earth if what a wave is a disturbance of a medium? So essentially what I'm asking is, how did light go from the sun to the earth with nothing to travel through? Waves need something to travel through. Now, this wasn't a problem to scientists at the time, because at the time they did not believe in the vacuum. Instead, they all thought the universe was made up of a substance referred to as the ether, that the universe was filled with this substance, and there was nothing called empty space at the time. Now, an experiment happened in the late 1800s to prove the existence of this ether and to show that it was there. The basic idea of this experiment is that as the Earth goes around the sun, it will occasionally go against the ether and go with the ether, depending on the time of year. So this team of scientists, led by these two gentlemen right here, Michelson and Morley, conducted an experiment to show that light travels at slightly different speeds depending on the time of the year, based on the direction that the Earth was moving around the sun. Now, as you can see from the title of this slide, this was considered the great failure of physics, the great failed experiment, where in their experiment showed that the thing they're trying to prove, the ether, did not exist. Now, this took a long time to convince people, because at this time we've had 200, 300 years of believing that that light is a wave and that the ether must exist to allow that wave to pass through it. So now to take that away, it took a long time to convince scientists of this. This experiment was repeated again and again from different teams. Different experiments were thought of to increase the precision of it. And keep in mind, it takes years to do this because we're talking about the Earth revolving around the sun. It takes about a year to conduct even one trial of the experiment. But eventually everyone was convinced that the ether did not exist. Now, this leads to a problem. What's light? If it needs to, waves need a material to go through, and now we don't have a material, what can light be? This is almost as bad as the ultraviolet catastrophe in physics, but we'll get into that one another day. So, during this time, Einstein was working on light himself. Now, he was looking at a totally different thing that light has, and eventually this actually led to solving the problem for what light is. And let's take a peek at this. What Einstein was working on was referred to as the photoelectric effect. Now, if we're looking at the photoelectric effect, it's essentially we take a bright light, we shine it on a metal, and when we do that, electrons get ejected out of that metal. The reason being, in our classical view we have here, is the electrons are absorbing the energy that the light has, and then once it gains enough energy, it can leave the pole of its atom and go flying off and do its own thing. So a high frequency light like blue or any high frequency light will cause these metals to eject electrons. Now, just as a quick note, different metals require different frequencies to make this happen. That's for a topic for another day as well. Another important note about the photoelectric effect is the brighter the light, the more electrons you get off of it, which should make sense. We have a higher amplitude light, we have more energy, we should be getting more electrons. But what gets interesting with the photoelectric effect is what happens when you change the frequency of the light. You see, if you do the same thing with red light and shine a red light on a piece of metal, what you get is no electrons being ejected whatsoever. Now, you could be thinking, oh, okay, it doesn't have enough energy to cause the electrons to eject. Well, what really baffled scientists was, what if we amped up that red light? What if we put so much energy in that red light, it made such a bright red light? Well, no matter how much energy they poured into making that red light, no matter how bright it was, no electrons got ejected. And scientists really did not understand that at the time. They were able to categorize and show this stuff, but they weren't able to show why the red light, even the high energy red light, wasn't able to eject electrons when a rather dim blue light could. It wasn't until Einstein finally came up with his theory on the photoelectric effect, and that is that light acts as both wave and particles. And this helped both explain the photoelectric effect, but also helped to explain the problem that scientists were having at the time. And he actually won his Nobel Prize in the photoelectric effect in 1905. Now, this often confuses a lot of people, because when people think of Einstein, they think of things like relativity, they think of things like gravity, and all the kind of weird nuclear physics that Einstein was working on. Didn't he win his Nobel Prize for that? Why would he win it for something, the photoelectric effect? Like, that's important at all. Well, keep in mind, at the time, physicists were pretty much freaking out. We had this idea of how light worked for hundreds of years, and then to have that taken away from one experiment showing that, well, that's not how the universe worked, there's a lot of disarray at the time. And for Einstein to come up with an idea that fixes that problem and has some pretty profound effects that we're going to get into in the next couple of slides, it was a very big deal for physics, which is why he won his Nobel Prize in that, and nothing else, no other thing that he worked on, he won his Nobel Prize for. So just to show you kind of how of a big impact this photoelectric effect and explaining the photoelectric effect is. So let's talk about wave-particle duality. What does it actually mean? Well, in Einstein's view, he thought of light as individual packets, which he referred to as quanta. Now, quanta comes from the prefix quant, which means number. We've done quantitative labs, for examples, which are labs that work with numbers. So what a quanta is just an individual exact number of light. Versus before, if you think of light just as a wave, it's continuous. But now Einstein's describing as a distinct number of light. And these quanta were eventually called photons for light. Now let's look at a quanta. So a quanta is an individual packet of light. So a red photon is something that has a long wavelength, low frequency. We've already learned about this. But what Einstein did is he connected energy to these quanta. So he found that red light and red photons have low energy, while blue light, with its short wavelength and high frequency, have a high energy. And he talked about the fact that light behaves like a wave when it's traveling through empty space or through a material. However, once it actually starts to interact with matter, starts to start hitting things, that's when it will begin to act like a particle. So let's look at the photoelectric effect from Einstein's point of view. So in Einstein's point of view, what those light is made up with is those individual packets of photons as they move down. So blue light, with its high energy and high frequency, has enough energy to hit the atoms of the material and cause the electrons to eject outwards. And if you made the light brighter, what you actually were doing, you weren't changing the energy of each individual photon, but instead you were simply creating more photons. So you have more photons coming out of the light, which is causing more electrons to eject outwards. So increasing the brightness of the light, increasing the amplitude of the light, what that's actually doing is it's increasing the number of photons, which in turn would increase the number of ejected electrons. But remember, the important thing with the photoelectric effect is what happens with those low frequency light and why that doesn't work. Well, let's take a peek with Einstein's point of view. So we have the light come in, we have the individual red photons coming in, and as they hit the material, nothing happens. And the reason why nothing happens is that each individual photon does not have enough energy to actually get the electron to excite it, to get it to ionize and come off of its atom. Now, even when you increase the light, if you give the light tons of energy, all you're doing is you're making more photons. But still, each individual photon does not have enough energy to actually knock off an electron. So it doesn't matter how many you have, you'll never have enough energy to actually cause the electron to leave its atom. So changing the brightness has no effect on the experiment. Now, this is a pretty big deal because now this helps explain why our really high energy red lights can't do what relatively low energy blue lights can do. Now, let's take a look at the basics of wave-particle duality. A lot on this slide. To begin with, light acts as both a wave and a particle. That's where the wave-particle duality name comes from. And light has a lot of wave properties that we talked about at the beginning of the year. Things like polarization, the polarized sunglasses. Things like diffraction and interference, which we're seeing on this picture over here. Light coming in, it bending off, it diffracting out into this distinct pattern. And then the light hitting each other, interacting with each other, and causing a distinct interference pattern that we see. So light has these many properties. Also the Doppler effect, another very classical wave-like thing that light undergoes. We've talked about red shift and blue shift of stars before. That's the Doppler effect. Now, the particle property that Einstein introduced was the photoelectric effect, was the fact that these photons carry with them momentum. Now, this is a pretty weird thought because if we think of momentum, we think of P is equal to M times V. Well, to have momentum in what we've been working with since the beginning of the year is you need to have a mass, but light does not have mass. So light carries momentum while at the same time not carrying mass, which is an interesting idea, which is why it took so long to figure it out. What Einstein worked with is the fact that as a photon comes in, it can hit an electron, and that can cause that electron to gain momentum, and that photon in turn will lose some momentum. We've talked about collisions before. So, sorry, one second, my cat's freaking out. Sorry about that, my cat really wanted to sit on my lap. So, where was I? The photon hits the electron, which causes some of the momentum from the photon to go to the electron, causing it to move. Now, if you have enough momentum, that essentially knocks it out of the atom, which is the photoelectric effect in a nutshell. Now, an important thing to keep in mind is the fact that at this point, our energy of our light waves come from two different things. Now, when we're in the wave unit, we just thought of energy in the form of amplitude. The higher amplitude, the more energy there is. But with Einstein's new view, we actually have two relationships. So when we look at the amplitude of something, what we're doing is we're essentially determining the number of photons that we have. So a high amplitude thing has many more photons than a low amplitude thing. So you can still get a high energy red light. You just have more photons when you do that. Now the frequency is also important to the energy of light, and this is Einstein's new thing. So the lower frequency photon has less energy than the higher frequency photon. And this relationship, as described by Einstein, is given by this formula right here. The energy of a photon is equal to h times the frequency. And this h is a constant referred to as Planck's constant right here. Now, this is the smallest number we've ever worked with in this year and will work with this year. You can see it's times 10 to the minus 34, and a very incredibly small number. So when you take this Planck's constant, which is named after, by the way, the scientist who came up with it, and multiply it by the frequency, you get the energy of the photon. And that is this part of the formula right here. So it's a very easy formula to use, but keep in mind it has some pretty profound meaning as we're figuring out how frequency of a light is related to its energy. Now, it also has the second part of the formula over here. Now, this is actually something that's on the reference table, and I think it's nice that the Regents gave it to you. Where this comes from is our formula V is equal to the frequency times the wavelength. Now, if we're talking about light, our V, our speed, is given by c, or the speed of light, is equal to frequency times wavelength. If I solve this for frequency, I get that the frequency is equal to the speed of light over the wavelength. And if I take this right here and plug it in for frequency, I get this relationship right here. So potentially, you can use either one of the two formulas or two parts of the formulas. If the problem has frequency in it, you're going to use the frequency side. If the problem has wavelength in it, you're going to use the wavelength one. That's pretty much it. It's a very easy formula to use. Just keep in mind that the numbers you're going to get are generally going to have some crazy big scientific notation or crazy small scientific notation. Your Planck's constant is always going to be very small. Your frequency will tend to be very large, generally times 10 to the 14th for visible light, if you remember that from the beginning of the year. And your energies are also going to be pretty small as well. So expect to see some scientific notation for your answers here. Now, before we begin doing some practice with that equation, I do want to take one aside, and that is that particles themselves also have wave-like properties. So particles, like light, also has wave-particle duality. They do both. This is definitely a very weird idea to think about because you're made up of particles. So am I saying that you also have some wave-like properties? Yes, kind of. They're very small. See, just like light, objects that have mass also have wave-like properties, but they tend to be so small that we can never detect anything with it. Only if you get really, really small particles like electrons can you start to see some of these effects of wave-particle duality actually happen. And the reason why is the relationship between the wave-like properties, or the wavelength, of a physical substance, something with mass, is equal to Planck's constant, which is again times 10 to the minus 34th divided by momentum. And momentum is, of course, has mass in it. So if you have something that has a really high mass, and this is already a really, really small number, you're going to get an incredibly small, basically non-existent wavelength. Something, however, with electron, if a very small mass, can you actually start to see some of the effects. Now, I do want to point out that this formula right here is not one that you have to know. It's not on the reference table. It's not one that you're going to use. I just want to show you why this effect happens only with electrons. Or it happens with everything, but we only really notice it with electrons. There's a famous experiment called the double slit experiment, where we've done this with waves earlier on in the year. But it turns out if you take electrons and fire them through a double slit, what the hell will happen is they will actually make an interference pattern much like waves do. And that shows that electrons also have these wave-like properties. And this extends into other types of matter as well. However, again, the more massive the matter, the less the effect that we're going to notice. Okay, so we're going to do a little bit of whiteboard work. I'm going to basically do these questions in front of you guys just so you can see how to do these questions. All right, let's start on the first one. So in this first question, we have a lightsaber that's releasing photons with an energy of 1.9 electron volts. Now, I haven't talked about electron volts yet in this video. However, it's just another unit for energy. Now, what this unit is used for is when we have very, very small amounts of energy, basically the amount of energy that photons and electrons, stuff like that has, rather than having to constantly deal with scientific notation saying, oh, that one has, 8.3 times 10 to the negative 16th amount of energy or something like that. Rather than having to constantly deal with scientific notation, what scientists use is another unit instead, just to make communication easier between scientists. You guys probably remember that back in chemistry when you used the universal atomic unit for mass and you use grams. Both of them are very nice units to use. Just saying, oh, how much does that element weigh? Oh, it weighs, 12 is very helpful. And this is essentially the same idea that we have here. So the first part of this question is for us to determine the amount of energy the photon has in joules. Basically, we just need to convert between these electron volts in joules to do this. Now, in order to do that, we just have to use this section of the reference table. So on the front page of the reference table, not only do you have a lot of variables like Planck's constant, which I'm sure we'll be using in this whiteboard work, we also have some unit conversions as well. And as you can see, the one above that, we have the electron volt right here. So 1 electron volt is equal to 1.6 times 10 to the minus 19 joules of energy. So for us to convert this 1.9 electron volts into joules, we just have to take our 1.9 EV. By the way, lowercase e and uppercase v is the, what's that word I'm looking for? Is the letters we use for the unit to represent the unit. And we're going to multiply that by our 1.6 times 10 to the minus 19 joules per electron volt. And when we do that math out, we get 3.04 times 10 to the negative 19 joules worth of energy. So that's our first question. That's just how much energy it has, but now in joules. Now, just like any other unit or any other equation, we have to make sure that we're in the SI system of units to do our math, which is why we're asked to do the conversion here. Though it's easier for us to discuss our energies in electron volts so we don't have to deal with the scientific notation, we will eventually have to convert it back into our SI units so we can use our equations, so we can use our different constants and stuff in that SI system. That's why we had to do this conversion to start with. The next one is determine the frequency of the photon. Well, that's going to be our new equation we just learned. Energy is equal to H times F. By the way, if you haven't noticed, in the reference table, we're actually in a new section titled Modern Physics. It does not have that many formulas, so it's not too hard to pick the right one that you think we need. But we have the energy is equal to H times F. Well, if we have the energy of 1.04 times 10 to the minus 19 joules is equal to our H, which is 6 points, nicely right down here at the bottom. 6.63 times 10 to the minus 34 joule seconds times our frequency. That means if I do the math, our frequency is equal to 4.59 times 10 to the 14 hertz. It's generally a good idea to know, the rough answer that you should expect for a problem. For something in modern physics, that can be kind of tough. But when it comes to finding frequency, however, you'll notice that our answer will quite often be times 10 to the 14th or around that area, because times 10 to the 14th is in the visible light, and a lot of our questions like to deal with our visible light questions. Doesn't mean every single question will, but quite a lot will be within that range. So if you see something that's times 10 to the 14th, there's a very good chance you did the question correctly. Now it says determine the color of this lightsaber. So in order to do that, you just have to look on the reference table at the electromagnetic spectrum and see what this, where this lies on that spectrum. And I believe, if memory serves, 4.59 is right in the orange area. So this is our answer for part B. This is our answer for part A. And just because I'm running out of room here, we have our orange for part C. And again, all you have to do, look at the reference table, open it up, look in the electromagnetic spectrum, and you'll see that this 4.59 falls right in between the two ends of orange. So explain what wave particle duality means for a photon. I'm not going to write down the answer here. I'm just going to talk about it. What wave particle duality means is that a photon has both wave-like properties and particle-like properties. Some examples of our wave-like properties are diffraction, interference, polarization, things like that we only see for waves and we don't see for particles. However, our big particle-like property is that it contains momentum. Now, obviously, it's a big deal that it can travel through the vacuum of space, but when we're talking about this kind of thing, it's the momentum we like to focus on as our particle-like property. Finally, we have calculate the, just get that stuff off of here. Calculate the wavelength of a photon having 3.26 times 10⁻19 joules of energy. This is another very straightforward question. The only main difference here is we're going to be using the different formula for it, and that is hc over lambda. We're going to use the same variables that we had before. We have our h, which is 6.63 times 10 to the minus 34 joule seconds, times our speed of light. If you don't have that memorized, don't forget it's at the top of that front page of the reference table. 3 times 10 to the 8 meters per second, all over the wavelength, and that's equal to our joules, which is 3.26 times 10 to the minus 19. Now, if I solve for lambda here, which is just this stuff divided by this, basically, these end up switching places. And if I do that math here, one second, I'm just going to put something in the way because that's how I can see my answers. We get 6.54 times 10. So I'm going to write that down. 6.54 times 10 to the minus 7 meters. Oh, and I'm sorry, I wrote energy for that. That's not what I want. I was solving for wavelength there. The wavelength, which makes more sense, is 6.59 times 10 to the minus 7 meters. Again, minus 7, that's probably in the area that we're going to see most of our answers for our wavelengths of photons. That's basically it. At this point, I hope you feel comfortable with the practice. If you have any questions, always feel free to contact me, email, Google Classroom, whatever it needs to be. Thanks for watching.